We've looked at astrometry and photometry. Time to look at the third main tool in Stella, spectroscopy. That's the study of stellar spectra. The basic idea is that the stream of light from a star is made up of different wavelengths and frequencies. Visible light has wavelengths between about 350 and 700 nanometers. Newton used a prism to separate light into a rainbow of colors. Nowadays, people use reflection or transmission gratings to separate the light. In a modern spectrometer, the rainbow falls onto a bank of electronic detectors that, just like our photometers, record the intensity of the light. But instead of just one number for the whole star, we get an array of numbers, one for each tiny wavelength band or channel. In Stella, point the telescope at your star as usual, then go to the Spectra tab. There you will see the spectrum of the star. This is our old buddy S400. These dark lines, absorption lines, read more about them in the background or search online, correspond to particular elements. You figure out which elements by comparing spectra from what are called discharge tubes of known materials. For example, we can choose hydrogen from this menu to choose a hydrogen discharge tube. A discharge tube makes bright lines, emission lines, instead of dark absorption lines, but the wavelengths are the same. So you can see that this bright line in the hydrogen spectrum corresponds to this dark line in the solar spectrum, or at least it appears to. Let's make a graph of the spectrum. To do that, press the big Save button next to the spectrum you want to save. To make a graph, we need a table of data. Of course, that's up here in the Tables menu, and there's a table called Stellar Spectra. So I create that table, and I create a graph. Now I'll put wavelength on the horizontal axis for the graph, and intensity on the vertical axis. And there is a graph of the spectrum of S400. If you want, you could even connect the dots. Up here at the top end is that hydrogen line. And in the table, I've selected it, in the table you can see its wavelengths at 654.5 nanometers. The next point isn't until 658, so this is a pretty low resolution spectrum. Let's zoom in. To zoom in, click in the bottom spectrum. With every click, you zoom into the area you clicked on. The top spectrum stays the same, and the bottom one shows a higher resolution spectrum. The gray thing in the middle shows you what part of the upper spectrum is being represented down here. Click in the gray thing to zoom back out. The wavelength range also appears in these boxes if you want to just type them in. I'm going to zoom in a little farther. See, here's that line, and here's where it is up above. When I click Save again, Stella records 100 points for our high-res spectrum. If I just want to see that data, I can select it down here. This is the third run. And you can see that the points I got, all zoomed in, are selected over here in this graph. Naturally, all I have to do is hide the unselected cases and rescale. Now I can see that part of the spectrum in greater detail. If you want to compare directly with the hydrogen spectrum for the lab, you can click Save for that as well. Stella keeps the resolution the same for both spectra. Now that's interesting. It looks as if the lines are in different places. Let's plop name into the middle so we can tell which one is which. You can see that H is the graph that goes up, it's the emission spectrum, and S400 has the dip, it's the absorption spectrum. And now we'll zoom into the plot itself to see the data spread out a bit. One way to do that is to hold down the Option key while pointing at the axis. the cursor changes to a magnifying glass and you can click in the axis to spread the data out, like that. This difference in wavelength is too big to be a mistake. It's because of the Doppler effect, which is mentioned in the background and explained on the web. Be sure to look that up. Because the star's line is at a shorter wavelength, we say that it is blue shifted. It means that the star, S400, is coming towards us. If it were at a longer wavelength, it would be red shifted and moving away. Question is, how fast is it coming towards us? The change in wavelength is proportional to speed. That Greek letter lambda is traditional for wavelength. Maybe it's because L, like lambda, is for length. Delta lambda is the change in wavelength. Let's figure that out. Back in the graph, we see the lab wavelength, the rest wavelength, is 656.256 nanometers, based on this emission line. But in S400, the middle of the absorption line is at about 656.053. The difference between those two numbers, 0.203 nanometers, is delta lambda. Over in Desmos, we'll solve the equation for V and plug in numbers. Here's our original proportion. Here is the equation solved for V. Let's see. And here we're plugging in the numbers. We have 0.203 for delta lambda. Lambda is the wavelength itself, 656.3 nanometers that we used. Let's see, 0.256. C, the speed of light, that's 3 times 10 to the 8th meters per second. But frankly, stellar speeds are usually in the kilometers per second range, so we'll just use C as 300,000 or 3 times 10 to the 5th kilometers per second. And there you have it. Desmos tells us that the velocity is about 93 kilometers per second. Which direction? Because the line got shifted towards the blue, it's coming towards us. Traditionally, we assign that a negative value. Red shift will be positive, blue shift negative. One final note. We can now study the velocities of stars in 3 dimensions. Proper motion tells us about velocity perpendicular to our line of sight. That is, as you're looking at a star, x is left and right, y is up and down. The Doppler shifts tell us about motion parallel to the line of sight, towards us and away from us. This is also called radial velocity. And Stella awards badges for good radial velocity measurements. So once you've measured a couple of them, you won't actually have to go through the trouble of measuring the lines again.